Hello, I welcome you all to this another interesting screencast, and the problem reads: determine the components of reaction that the thrust bearing A and the cable BC exert on the bar. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Like we have always said, when you have either a journal bearing, a thrust bearing, for a thrust bearing, it is not free to move in this direction, in the y direction. Therefore, we are going to have a reaction in the y as well. For a journal bearing, it is free to move along the y-axis. This is a thrust bearing, so we are going to have a reaction along the y direction. But because we don't have additional supports, okay, elsewhere, okay, we only have this cable which is exerting some tension force at B. So we cannot consider this as a support, right? And because we don't have supports on this particular structure, we expect the moments, okay, to exist about the z-axis as well as about the x-axis. But if we had additional supports, okay, elsewhere, if we had, let's say, maybe a journal bearing, or if we had, let's say we had a roller, maybe here at maybe a support here, a roller or something, then we could not have included the support moments there, okay, the reaction moments. So we are going to have the reaction moments at A in the z direction and x direction because we do not have supports, okay, along the length of our structure. We do not have additional supports other than the thrust bearing, right? So we have the reaction force. We're going to have the reaction force AZ, but we also have the moment reaction. I'll denote it by double arrows like so along this direction. Then I'll call this one as let me call it as MA Z. Alright. Then I'm going to have another reaction in this direction that I'm going to call AX, but I also have a moment in this direction that I'm going to call MAX. Of course, along the y-axis, we are going to have another reaction in this direction, which we are going to call AY, but the moment will be 0 because it is free to rotate, but it cannot just move in the y direction, but it can rotate. So we are not going to have any moment. And then we are going to section this cable, all right, to section it. And if we sectioned it, then we are going to have some tension force BC like so, okay. So these are the support reactions that we are going to have for this structure because we do not have any other support on the body of the structure. If we had additional supports other than the thrust bearing along the longitudinal length or along the body of the structure, we could have neglected the couple moments or the reaction moments. All right. But this time around, do not neglect them like we did in the previous case because we do not have additional support we do not have any additional supports other than the thrust bearing at A. I hope that is clear. So how many reaction forces do we have? We have 1, 2, 3, 4, 5, 6. Okay, and we have also 6 equations of equilibrium, because this is a rigid 3D rigid body equilibrium problem. It's a 3D rigid body equilibrium problem, and for 3D we have 6 equations of equilibrium, and in this case we have also 6 unknowns, right? So let's apply them and then see how far we are going to go. So summation of forces in the x direction. What do we have in the x? We have ax. What else? Just ax is equal to 0 pounds. All right. And then we have summation of forces in the y. What do we have in the y? We have ay. What else? ay equal to 0 pounds. Then we have summation of forces in the z axis. What do we have? Here we have AZ, then we have BC, then we have minus 80 equal to 0. Okay, and then summation of moments about the x-axis. What we have? We have MAX, okay, right, and then of course, AZ and AX will not cause any moment about the x-axis because they are lever arm. AZ and AY will not cause any moment about the x-axis because their lever arms are equal to 0. And AX will not also cause any moment about the x-axis because it is parallel to the same axis. Alright, when you have a force parallel to the axis, then you cannot have a moment along that axis due to that force that is parallel to that axis. So when you have a force that is parallel to an axis, it cannot cause a moment, okay, to an axis parallel to itself as a force. Okay. So summation of moments about the x-axis is equal to 0 max, and then we'll have 80 using the right hand thumb rule. It is going to cause a negative moment about the x-axis, so it will be minus 80 by 6. Okay, and then BC will cause a positive moment, so it will be BC by 6 equal to 0. Alright, so let's move to the summation of moments about the y-axis equal to 0. What do we have? Again, about the y-axis, AY will not cause any moment about the y-axis because it is parallel. AZ and AX have their lever arms equal to 0. Therefore, the only forces that will cause a moment about the y-axis is AT and BC. Okay. AT, using the right hand thumb rule, it is causing a negative moment, so it will be minus 80 by 1.5. Okay. And then we'll have a plus moment due to BC by the lever arm for BC is 3. Okay. Then equal to 0. Therefore, BC from this equation will give us, what will be BC? We have 80 by 1.5 divided by 3. So this gives us BC equal to 40 pounds. Okay. Right. Once we found 40 pounds, we can move on and plug it in the other equation. But let me just apply the last equation, which is summation of moments about the z-axis. About the z-axis, AZ will not cause any moment about the z-axis because it is parallel to the same axis. AX and AY have their lever arms equal to 0. AT and BC are parallel to the z-axis, therefore they will not cause any moment about the z-axis. So the only moment that exists there is just MAZ, which in itself is equal to 0. Great. So we have found BC. We said BC here is equal to 40. So with that BC, we can therefore find what MAX is. And our MAX is just going to be equal to, we have minus 80 by 6, then plus 40 by 6. So this gives us a 240 Newton meters. We have BC there, we move up there. We have BC equal to 40. Therefore, our AZ is just going to be equal to, we have a 40 minus 80, which gives us a 40. Therefore, BC is just going to be, AZ is just going to be equal to 40 newtons. So let's write this. We have BC equal to 40. Okay, this is 40. Okay, just at one point is enough. And then we have AZ is equal to 40. And then we have AY is equal to 0. AX is equal to 0. MAX is equal to 240 newtons meter. MAZ is equal to 0. Right. Let's check whether this is equilibrating. In the x-axis, AX is 0. In the y-axis, AY is 0. The z-axis, we have a 40. And then we have a 40, 2 40s up, which gives us 80 and an 80 down. Right. And we have this moment about the x-axis. The x-axis, right? So we have 80 by 6, and then a 40 by 6, giving us, alright, so we have minus 80 by 6 plus 40 by 6 plus 240, of course, gives us a 0, right? So everything seems fine. So let me just correct the units. So these ones, this is pounds, this is pounds, pounds feet. Okay, this is pounds feet. Great. So we have AX is equal to 0. We have AY is equal to 0. We have AZ is equal to 40. We have MAX is equal to 240. We have BC is equal to 40. We have MAZ is equal to 0. This is really about it, and I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.